Hello, everyone, and welcome to day 28 of Jamb Physics in 40 Days. The Jamb Physics in 40 Days is a series that is brought to you by Oyalen, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you should be able to get all the necessary tools that will help you ace Jamb Physics. So, peradventure, you are thinking of writing the Jamb exam or preparing for the exams. These videos is specifically made for you, especially when physics is one of the subjects you've selected to write in that exams. So you do not want to miss any of the videos in this series. Please do well to check out the videos from day 1 till the end. This is day 28, and each of those videos we discuss the individual topics that are in the Jamb physics curriculum, giving you a crash course to it while we solve past questions and give you tips that will help you solve such kind of questions with greater accuracy each time. This is why it is important that you check out each of the videos. And please, if you're not subscribed to the channel, I want to encourage you to please click the subscribe button. That will be your way of helping us to be able to continue to make more helpful content like this. So please click the subscribe button, and you can also click the notification bell icon so that you get alerted every time we put out a new content. And please do not forget to like the videos and also share it with all those that are on your contact so that they too can have access to this helpful content that we are making. So please share it, ensure it goes as wide as possible. And to practice even more, I would encourage you that you click the link in the description box of this video to download the Exam Fun app. Now, that app is created with you in mind to infuse a bit of fun into your learning time. We do not want your learning time to just be a drag. We want to make it as enjoyable as possible. So please download the Exam Fun app today, and then you can also make your learning time more fun. And what is even more interesting about it is that it is not just a fun app, it is also a rewarding app, which rewards you based on the number of questions you solve correctly. So that is, as you are learning, you can also earn with the Exam Fun app. And if you have any question at all on what we are doing so far, or perhaps during your study time you came across a question that you would like some help with, please put it in the comment section and we'll definitely attend to every one of your comments. Now, what we are doing in day 28 is electrostatics, and what is expected of every Jamb candidate taking the exam regarding this topic is that you should be able to identify charges. Now, when it comes to electrostatics, we recognize two types of charges. We have positive charge and negative charge. You should be able to identify this. Now, to be able to create positive charge, what you need to do is to rub a glass with, when you rub glass with silk, you produce positive charge. Then when you rub ebonite with fur or hair, you create the negative charge. Those are the two ways you can create positive charge and negative charge. Now, even when you are at home, you can also create these charges around you. These are some things that happen to us on a regular basis. Like, for example, when you rub your pen on your hair, especially dry hair, when you rub it vigorously, it becomes negatively charged. And that way, you can even pick up bits and pieces of paper using that charged pen. And there are so many other things like that we do. Like, for example, when you're walking on dry rock for a long time, you sometimes observe that by the time you put your hand close to a metal object, you feel this slight shock on your finger. It's also one of those observations that we get for electrostatics. Or during dry weather, sometimes when you lift up your clothes from your body, you feel like a rattling sound on your skin due to charges that are coming together to discharge each other. That is also another observation on electrostatics, and you can use these to get different types of charges and identify whether it's positive or negative charge. Another thing that is expected is that you should be able to use the electroscope, especially the gold leaf electroscope, to examine charges, whether it is a positive charge or a negative charge. Now, you should be able to tell what happens when you bring a positively charged body to an uncharged gold leaf electroscope. What happens when you bring a negatively charged body to an uncharged gold leaf electroscope? What happens when you bring a positive charge to a positively charged gold leaf electroscope, or when you bring a negatively charged body to a positively charged gold leaf electroscope, vice versa? That is, when you know the charge on the electroscope and the charge that you are bringing to it, you should be able to tell what happens based on whether the leaf diverges or it collapses. It's something that is also expected of every candidate taking the exams. Thirdly, they expect that you should be able to apply the Coulomb's inverse square law of electrostatics to solve problem. Now, the inverse square law can be combined together to give you this equation where we say F equals K Q1 Q2 over R squared, or we just say F equals 1 over 4, this is 1, 4 pi epsilon naught, then Q1 Q2 over R squared. And please take note that your 1 over 4 pi epsilon naught is 9 times 10 raised to power 9 in value. So working with this, you should be able to solve quite a number of problems concerning the inverse square law of charges. Now, they also expect that you should be able to identify electric field flux patterns of isolated and interacting charges. Like what happens, how can you tell the line of force of an isolated positive charge? Say, for example, this is an isolated positive charge. The line of force around it tells us the direction and the strength of the electric field that we are looking at here. This is an isolated positive charge which has its own field. And the line of force shows how strong the field is and the direction each of the charge is moving. So since this is a positive charge, you're going to experience a field that looks like this. Now take note, the direction is always away from the positive charge. It's always away from a positive charge. Meaning if I should do an isolated negative charge, it's going to be the same thing just like this. If this is the negative charge, the difference is just the direction. Okay, so all you just have to take note for cases like this is the direction. So because this is the negative charge, the direction of the line of force is going to be towards the negative charge. Towards the negative charge like this. Now, what happens when you when there's an interaction between two charges? Now, if they are both the same charge, whether positive, positive or negative, negative, there's going to be repulsion. So I'll give you an example with positive, positive charge when they interact, when two positive charge interact. So this is positive charge, positive charge. Remember, the line of force is still going to be like so. But what happens is that you start seeing repulsion occurring like this. You see this shows repulsion. And remember, since it's positive, the direction is away from the charge. Away from the charge. Okay, so if you're going to do the same thing like this, but you want to use negative charge, all you have to do is this same diagram is what you draw. The difference is that the arrow will now be pointing towards the charge if they are negative. Okay, so what is to take home from this is that when you have the same charges, similar charges, there is repulsion occurring. Now, this is what leads to the fundamental law of charges, which says that similar or like charges are going to repel, while unlike charges will attract each other. Okay, so now that means if I should bring a positive and a negative charge together in a field like this, positive, negative, what will happen is attraction. Attraction is going to occur like this. Okay, and do not forget the direction from the positive charge is away from the charge. Okay, while to the negative is in the direction of the charge. It's going to be coming into the charge, which is why the arrow here is just going to be like this. Okay, that shows that this positive charge is forcing its way to meet the negative charge so that they can be together. That is force of attraction between two dissimilar charges. So it's important that you are able to describe this kind of interaction among charges in a field. Now, another thing that is expected of you is that you should be able to analyze the distribution of charges on conductors and how it can be used as in lightning conductors. Now, I'm sure you would have observed this where you see tall buildings. You often see something that looks like a spike at the top like this. At the top of tall buildings. It's always attached to the top of it. Now, this is what happens. Because of electrostatics in the cloud and the earth, the interaction, there's often charge discharge, which leads to what we know as lightning. What you see as that lightning strike is actually charges, a positive charge jumping either from one cloud to the negative charge of another cloud, or positive charge in a cloud jumping to the negative charge on earth, and vice versa. It could also be positive from the earth going to negative in one of the clouds that is passing overhead. Now, the thing about this kind of interaction is that they always go to the closest charge to them, right? This is why when you are in a region where there are a lot of tall buildings, you see that the tall buildings are often hit by lightning strikes a lot. Take the Burj Khalifa for an example, which is the tallest building on earth. The number of lightning that hits it on a daily is so high compared to the short buildings. This is why it's always advised that when you are in a plane where there are no tall trees, no tall houses, when it is raining, you have to quickly find your way into a house, because there is every tendency that you could be hit by lightning when you are in a playing field, right? So in order to make sure that you avoid this kind of problems, this is why they put things like this on tall buildings. Now, what happens is this: when you consider any object at all, the way the charges congregate around it is in this pattern. Let me draw this here now. Look at this. If there are going to be distribution of charge around this, let's say positive charge, you will see that the number of charge around this curved part is going to be very little. Very little. But by the time you get to the sharp end, you see a lot of charge congregating around that sharp end. That is how charges are distributed on a body. So when you consider a building too, charges are distributed in a diffuse way around the building. But in order to reduce the amount of lighting that can destroy such a house, they'll put something like this that is very sharp at the top of the building, and then they connect this to the earth. Now, remember that the earth itself is supposed to be more like a sink, that is, can absorb as many charge as you give to it. So when this sharp object is at the top of that building, anytime any of the charges are going to discharge each other, by the time the lightning comes, it's going to attack the charges that are on these spikes of this particular structure you see here. So by the time the lightning hits this, it will then conduct it to the earth, making sure that the house itself is completely safe from that lightning discharge. So this is one of the principles that is used in that situation. And if you check out skyscrapers around, you will see that they even have multiple of this kind of structure around it like that, just to ensure that anytime there is a lightning discharge, it can arrest that lightning and transfer it to the earth. So this is what is expected of you by Jamb. However, for a greater detail of what we have just talked about here, I'll advise that you check out our video where we discuss electrostatics in more detail. Now, the difference is that this video is a prep video for Jamb candidates, and we believe that to be a Jamb candidate, it means that you must have gone through all of these topics at different levels in the secondary school. But if you feel that what you have learned about this topic is not full enough, I'll advise that you please check out the video. And not just that, please share it with so many others, because there's a lot of things in that video that can impact a lot of lives. So please share the video and also take time to watch it. You might be learning a thing or two from that video, because it has more detail on what I have just explained so far. However, since this is a Jamb prep video, we will now be moving to solving past questions on this topic, but it doesn't end there, because as I solve those questions, I will still be giving tips that will help you to solve questions like that with greater accuracy every time you come across such kind of questions. So if you're ready, get your materials and then let's solve some questions. This question says, aluminium is sometimes used as the leaf of an electroscope because it... Now, the primary reason why you would want to use any material as the leaf for an electroscope is the fact that it can actually conduct charges, okay? So this is why we use gold leaf. We also use aluminium as a substitute. However, despite the fact that silver is a better conductor than aluminium, it is not used. Now, this is mainly due to two reasons. The first reason being that first, silver is not easy to get, it's not readily available, and it's expensive because of that. And then secondly, silver has a higher density and is not as malleable as aluminium. So which means that despite the fact that we have aluminium is a good conductor as part of the option, it wouldn't be the correct answer in this case. The reason that we have to go for in a question like this is not because of its conductivity, but rather because it can be converted into thin sheet, which actually describes its malleability. So the correct option for this question is D. In which of the points labeled A, B, C, D, and E on the conductor shown would electric charge tend to concentrate most? Now, when you find a conductor, you find that the charges are distributed across it. However, the charges concentrate more around the sharp edges. So when you look at the body structure of this conductor, you see that all this charge will be very scarce around this axis, but at this sharp end where we have E is where you tend to see the most of the charge. They concentrate at that sharp end E. That means the correct answer to this question is option E. This is a question that can sometimes be a little bit of a confusing one. So let's look at it and then simplify it so that whenever you see a question like this, you will know the correct answer without any doubt in your mind. Now the question says, the energy needed to move a unit positive charge around a circuit is called the... Now, when you look at the options provided, you easily rule out kinetic energy and electric energy. So these ones are completely wrong. And then you are left within two choices, whether it is electromotive force, also known as the EMF, or the electric potential difference. Now, the key to picking the correct answer in this case lies in a proper definition of these two terms. Now, electric potential difference is the energy required to move a unit positive charge from one point to another in a circuit. Remember, this is not about electric field. It is talking about a circuit. If we're talking about electric field, what is required to move a unit charge from infinity to a point within a field is electric potential, right? But in this case, we are looking at a circuit. It's only going to look at two ends, right, from point A to point B. Whereas the force that continues to move charge around a circuit, whether the circuit is open or the circuit is closed, is the electromotive force. So that makes the answer to this question option A. This question says a positively charged rod X is brought near an uncharged metal sphere Y and is then touched by a finger with X still in place. When the finger is removed, the result is that Y has... So let's visualize this and explain what happens step by step so that we can get to the right answer. So let's take this to be a metal sphere that is, according to the question, that is uncharged. Now, for it to be uncharged or neutrally charged, it means that the number of positive charges and negative charges are equal. So I'm just going to put a series of charges here, positive, negative, positive, negative, positive, negative. So it is now neutral. Okay? So now that it is neutrally charged, we have 3 positive charge, 3 negative charge. What will happen when you bring a positively charged rod near it? By the time I bring a positive charged rod, remember this is positive, 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 positive. Now what's going to happen is that all the positive charges will go to one end, making this now to be negative. This remains negative, this will now be negative, then all of these become positive like this. So because unlike charges are what attracts, so now we have negative, negative, negative on this end close to the positively charged rod, while all these positive charges will go to the far end here. Now that is explaining it up until this point. Now, and then it is touched by a finger with X still in place. By the time you bring a finger here, okay, now remember this finger is to the ground. Okay, now the moment you do this, what will happen is that negative charges begins to come. Now the negative charge will begin to neutralize this positive charge. As they begin to cancel out, it gradually becomes negative, becomes negative, becomes negative, until negative charge continues to accumulate on this sphere. Now by the time you remove the hand and this metal rod, what will happen is that the overall charge that is going to be, now we've taken this off, the overall charge that is going to be on the sphere now is going to be negative. And then when you compare that relative to the earth, you will see that the potential is also negative. So let's look at the option that tells us this. Now A says no charge and a zero potential. That's wrong. B says a positive charge and a zero potential. That's also wrong. C says a negative charge, yes, and a positive potential, no. Because compared to the ground, it has to be negative potential. And then D says a negative charge and a negative potential. So the correct answer here is option D. Which of the following is true of an electric charge? Now, before I go on to answer this, if you're yet to be subscribed to the channel, now would be a good time to just take a second to click the subscribe button, and you can also use that time to hit the notification bell icon so that you get alerted every time we put out a new content. And if you do have any question at all, please don't forget that you can drop it in the comment section, and be sure that we are going to attend to all of your comments, so keep them coming. And also don't forget that you can share our video also, because we really want to reach a wide range of audience that are in need of content like this. So please keep sharing, keep liking the videos. And if you have not downloaded the Exam Fund app, come on, download it. Just click the link in the description box of this video to download the Exam Fund app, and then spice up your learning time. And also, what is interesting about it is that it's rewarding, and you don't want to miss out that rewarding part as well. So download the app today and earn while you learn. I trust that you're going to do that, so thank you in advance for subscribing to the channel, for sharing our videos, for always bringing your comments, putting in your comments to support the channel, and also for downloading the Exam Fund app. Now, to answer this question, we have to pick which of these options provided that is true when we talk about electric charge. Okay, now the option A says positive charge means deficit electrons. Now, for an object to be positively charged, it means that there has to be a larger number of protons as compared to the number of electrons. Remember, protons signify positive charge, while electrons signify negative charge. So if a body has equal number of protons and electrons, it is said to be uncharged or neutral. But when there is positive charge and a deficit of electron, meaning there is lesser amount of electrons available, such an object will be called a positively charged object. So option A is actually true about electric charge. But let's not stop there. So let's look at option B as well. B says negative charge means excess of electron. That is also true. Based on what I've just said now, the highest number of, whether it's electron or proton, is what actually determines the charge of a body. So if there's excess electron, it means that such an object is negatively charged. So that is also true. So we see A and B are true. So let's check out what C says. Now, C says electric current means movement of electron. That is also true, because electrons in motion is actually what we call electricity, right? So electric current is electrons flowing, right? So that is also true. A, B, and C are true about electric charge. And D says all of the above. So yes, A, B, and C is correct. So all of the above is also right in this case. But E says A and B only. We have already established that C is true. Okay, so since C is true, it can't be A and B only. It can't be A, it can't be B, it can't be C. That leaves us with only one logical choice, which is option D. So we go with D for this question. Calculate the electric field intensity between two plates of potential difference 6.5 volts when separated by a distance of 35 centimeters. Now, what's important here is that you have to convert this into meters. So let's solve. To solve this, we're going to apply that electric field intensity E is given as V over D. And V is, according to the question, 6.5 volts, while the distance separating them is 35 centimeters, which is 0.35 meters. Now, when we find the electric field intensity, E, in this case, which is the electric field intensity, would then be given as 6.5 divided by the distance, which is 0.35. Now, what this would give us is 18.57 approximately and it is measured in Newton per coulombs. So the correct option to pick here is option A. When a negatively charged rod is brought near the cap of a charged gold leaf electroscope which has positive charges, the leaf, now this is what happens. Now take note that in this question we are told that the rod is brought near. It does not actually come in contact with the cap, it is just brought near. Okay, so that means if the question had gone further to say that the rod was then removed later, what will happen is that the original positive charges will later redistribute themselves. Okay, so but in this case we are only considering when it is brought near, not when it is taken away. So it helps us leave our answer to just 1 point. So at this point now, when you bring a negatively charged rod near the cap of a positively charged electroscope, now because of the attraction that occurs there, the negative charge will attract the positive charge, which will then cause the leaf to collapse. Okay, so that means the correct option here is option B. However, take note, if you find a question where it then says that the rod was then taken away, take note, they have to be first opposite charges for the leaf to collapse. Okay, because when the electroscope is positively charged, the leaf is going to diverge at that point. By the time you bring a different charge, it will collapse. If I had brought the similar charge, it's going to expand even further. Okay, that is diverge even further. But by the time you bring an opposite charge, like in this case, a negative charge, it's going to collapse. Then if the question goes on to say that that charge you brought was then removed, then the positive charge will redistribute again and then causing the leaf to diverge again. That will be a case for collapse and diverge again. But this one, we are limiting it to just when it is brought, so we keep our answer as option B, which says to collapse. Calculate the force acting on an electron of charge 1.5 times 10 raised to the power minus 19 coulombs placed in an electric field of intensity 10 raised to the power 5 volts per meter. So to solve questions like this, here's what we do. Now you should know that E equals F over Q. Now this implies that the force F is then the product of electric field intensity and the charge. So the force therefore becomes, now the electric field intensity is given as 10 raised to the power 5 multiplied by 1.5 now times 10 raised to the power minus 19. Now when you find the product here, this will give you 1.5 still. Now multiplied by 10 raised to the power. Now you have minus 19 plus 5, and that will give you minus 14. And force is measured in newtons, right? So if we have 1.5 times 10 raised to the power minus 14 newtons, that option is found in D. So we go with option D. In this question, it says an electron of charge 1.6 times 10 raised to the power minus 19 coulombs and mass of 9.1 times 10 raised to the power minus 31 kilogram is accelerated between two metal plates with velocity of 4 times 10 raised to the power 7 meter per second. Now the potential difference between the plates is, now to solve this question, we're going to equate this. Look at the solution here. Now the work done is actually the charge multiplied by the potential difference. And then this, it can be converted into kinetic energy. So we equate it with the equation for kinetic energy, which is half mv squared. Now please take note, this one is potential difference, capital V, while this small v is for velocity. So let's work with this. Now we can then make the potential difference the subject of the formula. Therefore, we would have mass times velocity squared all over 2q. Now, let's see what this gives us. The mass is 9.1 times 10 raised to the power minus 31. Then we multiply that by velocity. The velocity is given as 4 times 10 raised to the power 7. So we're going to put this in bracket and square that. Now, all over. Now we're going to look at the next part here where we're going to be having 2 multiplied by q. The charge itself is 1.6 times 10 raised to the power minus 19. Now to simplify this, this is what we're going to do. We can easily see 9.1 here. times 4 squared, that is 16. Then times 10 to the power of, we have minus 31 here. By the time you do this, you are going to have 7 times 2, which is 14. So plus 14 here. All over. Now what we have here is 2 times 1.6. Now 2 times 6 is 12. So 2 carry the 1. 2 times 1, that's 2 plus 1, and then we have 3. So 3.2 times 10 raised to power minus 19. So all that is left to do is to see what this gives us and then simplify this other part. So when we work with these indices here, we are having negative 31 plus 14. This minus 19 comes up and become plus as well. Now what you're going to see here is that by the time this comes up, you're going to be having 14 plus 19, and that is going to give you 23, right? 33, I mean. And then by the time you find the difference here, that will become 33 minus 31, which is 2. So we have plus 2 there. Now we have to do 9.1 times 16 and divide that by 3.2. Now you can just easily compute this using your calculator, but in the end, it should give you the answer, which is 4.55 times 10 raised to power 3 volts, which is in option A. If you're yet to be subscribed to the channel, please take a moment to click the subscribe button, and you can also hit the notification bell icon so that you get alerted every time we put out a new content. And don't forget that if you have any question at all, whether it's on what we are doing presently or it's something you found during your study time and you would like more explanation on it, please put it in the comment section. We will definitely attend to all of your comments. And also do not forget to share the videos, do not forget to like them, and do not forget to download the Exam Fun app to infuse some fun into your learning time. I trust that you're going to do this, so thank you in advance. Now, this question says, which of the following can conduct electricity owing to the presence of free mobile electrons? Now, materials that conduct electricity based on the fact that they have free mobile electrons are known as conductors. So we have to look at which of these is a conductor. Now, germanium is not a conductor, it's called a semiconductor. This is a semiconductor. Silicon is also a semiconductor. Grapefruit is not even a conductor. But here we have copper, which is a good conductor. So the correct answer here is option D. If two charge plates are maintained at a potential difference of 3 kilovolts, the work done in taking a charge of 600 microcoulombs across the field is, now the solution here is a product of the potential difference and the charge. That is, work done equals potential difference V and Q, so QV basically. So what we are having here is Q being 600 microcoulombs, that's 600 times 10 raised to power minus 6. Then we multiply that by the volt, which is 3 kilovolts, so 3 times 10 raised to power 3. Now when you work with this, you're going to have 6 times 3 is 18, so 18 times 10 raised to power minus 6. Okay, this is 6 times 3 is 18. Then the 100 here, so 1800 times 10 raised to power, this will give us minus 3. Now we can bring this down, that is 1, 2, 3 to give us 1.8, and it is measured in joules. So the final answer here is 1.8 joules, which is option B. If the distance between 2-point charges is increased by a factor of 4, the magnitude of the electrostatic force between them will be. Now, let's look at this. The relationship between electrostatic force and the distance between 2-point charges is given as F is inversely proportional to R squared. So if this is the case 1, in the second case, we then say F2 is proportional to 1 over, now the distance between them is multiplied by 4, so that will be 4R. Now square this. Now this means F2 equals 1 over 16R squared, which can be written as 1 over 16 multiplied by 1 over R squared. And 1 over R squared is actually the factor for the F1. So we can say F2 is then 1 over 16 of F1. So it becomes 1 over 16 of its former value, which is in option B. So that is option B is the correct answer. The electric field intensity in a place where a charge of 10 to the power of negative 10 coulombs experiences a force of 0.4 Newton is. So we are to find the electric field intensity in this question. So E equals F over Q. So applying that, E therefore becomes, the force is 0.4, while the charge is 10 raised to the power minus 10 coulombs. So we do 0.4 divided by 10 raised to the power minus 10. Now this would give you 0.4 times 10 raised to the power 10. And this is measured in Newton per coulomb. Okay, so working with this, we can bring this forward a bit, which will reduce this by 1. So E therefore becomes 4 times 10 raised to the power 9 Newton per coulomb. And the option that gives us this is option D. So we go with D. A student is at a height 4 meters above the ground during a thunderstorm. Given that the potential difference between the cloud and the ground is 10 raised to the power 7 volts, the electric field created by the storm is. Now, to solve this question, E is going to be V over D. So all we have to do is apply this. So let's solve. Now V is 10 raised to the power 7. Now we divide that by 4. Now basically what we have here is 1 over 4 times 10 raised to the power 7 and is in Newton per coulombs. Now this would give you 0.25 times 10 raised to the power 7 Newton per coulombs. So we can then bring this to be 2.5. Then you subtract 1 from this and say times 10 raised to the power 6 Newton per coulomb. So the correct answer here is therefore option B. An ebonite rod rubbed with fur attracts a glass rod rubbed with silk because. Now before we answer this, let's look at what will happen to the ebonite rod when you rub it with fur. Now that is one of the ways to create negative charges. Every time you rub an ebonite rod with fur, it generates negative charge. It charges the ebonite rod negatively. And then when you rub a glass rod with silk, it charges the glass rod positively. So by the time you are done rubbing both of them, they are now, ebonite rod is negatively charged and the glass rod is positively charged. And according to the fundamental rule of electrostatics, unlike charges will attract each other while like charges will repel. So now because the ebonite rod is negatively charged and the glass rod is positively charged, which means they have opposite charges, they will attract each other. So now looking at the options, the correct one is option A, which says the ebonite rod is negatively charged while the glass is positively charged. So we pick our answer as option A. Now folks, you can always get better with more practice, and one sure way to practice without the drag of always solving questions is to use the Exam Fun app. Yes, you solve questions, but it is created in a fun-like environment where you solve it at different levels, earning points, and also you can earn real money when you use the app. That makes your learning experience a lot more exciting than it used to be. So please download the app by clicking the link in the description box of this video to download the app either from the Google Play Store or the Apple Store, depending on the device that you are using. And if you come across any challenge, you have any question at all, whether based on what we are doing so far or it's on something you found while you were studying that you would like help with, please don't hesitate to drop the question in the comment section. We are here for you and we will definitely attend to all of your comments. And as always, don't forget to like, don't forget to share, and don't forget to subscribe to the channel. Thank you so very much for being part of the series so far. I'll be seeing you in the next video, which will be for day 29. Thank you so much.